Okay, today another hard problem. Subarrays with k different integers given an integer array nums and an integer k return number of good subarrays. A good array is an array where the number of different integers in that array is exactly k. Interesting. So nums length 2 to something, we got non-negative numbers. Number of... Okay, so my intuition is to count. Of course we can brute force, and for each subarray we can use like a hash map, and we could take this fixed L and then move R, and for each subarray we have a hash map and we put elements there, and if the size is under k, then we don't count them. Now if the size is k, we count them, and if size is over k, we don't count them. So what we can see, that answer is somewhat monotonic, that if we say that for fixed left bound, if I binary search for right bound, okay, that will not work, because I'm not sure how I would, because okay, I could do this for 1 in n log n, but distinct subarray queries seems kind of tough, no? I mean, I could do a segment tree which could answer such query in log n time, but there could be a lot of them potentially, so that query would take a while. Okay, so that's not a good idea, but what we can notice is that, let's say we, for L's equal to 0, we compute R0, which is the first right bound of first smallest subarray starting with L that has k, and then R1, which is the largest right bound of subarray, right bound of largest subarray starting at L that has k distinct integers. And now if we move L to right, well, what happens is that both of them have to move, so they either stay at the same position or move to right, and we can easily do that. So we can keep two maps for the smallest subarray and largest subarray, and I guess that's it. If we keep like a set, but it looks like the numbers are in a range 1 to n, which means we don't have to use a hash map, because the removal from there will be on, worst case. And we also don't have to use ordered set, which will have log n erase but also log n insert, but we can use a simple array and keep counts there. And now something is there if it has count over 1, and something is not there if it has count 0. So, and we can keep count number of elements depending on if the newly added value has occurrence 1 or whatever. You get the gist. So I think that's the way to solve this. So let's try to solve this. Let's grab the size of the numbers. Okay, and then I mean, we want, how many can there be such subarrays? If they say k is 1, and then each element has the same, the answer can be long, but looks like we should return int, but whatever. So answer is this, and then So we want to keep its count to, I want to do this, so int, so we'll have two counts and each of them two count arrays, and each of them will have size of n plus 1 since we want to index nth element. Now we have a left position, right position, and another right position, and we go until L is smaller than or equal to n and L plus plus on each iteration. So first of all, what we do is that well, let's say we are at L0, and what we want to do is while so we want to keep the but this keeps count of each element, but we want int element count. Okay, and now while R0 is less than n and L count 0, so the number of elements in the smallest subarray starting from L is less than k, then we're gonna do this. Cent of 0 of nums R0, what the hell, plus plus, and then if cent 0 nums R0 is equal to 1, then we want to do k plus plus, and then we want to do R0 plus plus, meaning, okay, we found some number, and if that was the first addition of that number, we added a new number, right? And that's nice. Okay, now we do the same, almost the same for, so while R1 is under n and L count 0 is more than or equal to k, meaning that it should represent last position 1 plus last position R such that LR is has k distinct integers, but we are also handling edge case where R1 becomes less than R0, so we have to do this, and the handling is quite similar. Like that, and now if that count is this k plus plus and R1 plus plus. Okay, and finally, after we have done that, what we can do is ans plus equals, let's multiply it by a long, and let's do R1 minus R0. Wait, I also have to have this check. So if L cent 0 is under k, or L cent 1 is more than or equal to k, essentially no. Yeah, this does it really matter? No, not really. It should be less, I think. And break. Okay, then here we return answer, and now what we are missing is What we are missing is that now we need to move L, which means that count of 0 of nums L minus minus count of 1 nums L minus minus if count 0 of nums L is equal to 0, then we do element count 0 minus minus, and same thing here, I guess. So what I can do is 0 1 index, great. And this will not work, but let's see. Compile error. What the hell, bruh? Here compile error, I already see it. And then I have a here compile error and here compile error. Or no? No, I'm just dumb. Now it works, maybe. So output is 0 in both cases. Interesting. R1, R0. Oh, because else and one. Oh. And why am I increasing K? Oh my days. Oh my god, bro. Terrible. Okay, almost got it. So L, let's see, R0. So K is 2. So this is the first position where we have more. Should be -1 actually. Or +1. No, +1. So 1, 2, 3, 4. Great, then you start here. 1, 2, 3, 1, 2, and so 1, 2. Let's see what survives here. Okay, so it's 1, 2, 1, 2, 1, 1, 2, 1, 2. That's fair. Then here we have 2, 1, 2, 1, 2. So 2, 1, 2, 1, 2, great. Wait. 3. I'm not sure I like this, to be honest. Wait, it shouldn't be 5, it should be 4. health and plus maybe that should not be here. Oh, now it worked. Great. So what I did was this was processing it also, like at 2 here it should end, right? So k is here, so the count of 1 nums are so element count 1 is 2 here, and we have pointer r1 is at this position, but the count was still lower than or equal to this. So it processed this also process first one after. So it also processed the real r1 and then did it r1 plus 1. So I added this check. So if the current count plus if the next element would be added to the count, so 3 would, so we don't want to move there. Great. Let's see on which cases this fails. I think it will on few edge cases, but I don't know. Oh, okay, interesting. So let's write my computer is very slow because I'm also on a call during this, so let's see, 2 pointers. So for a given fixed starting position for a fixed starting position L, how to find the subarrays for a fixed starting position L, how to find the subarrays with k distinct integers, let R0 be the ending position of smallest and largest such subarrays respectively. R1 be the R1 the contribution of, so the number of subarrays with k distinct integers ending at starting at L is R1 minus R0. How does can we use already computed R1 and R0 and R1 to compute them for starting position L+1. Of course we can. We just have to notice that the sequences, the R0 and R1 sequences for all starting positions are non-decreasing. That is because if L moves to L+1, the new subarrays, the shortened subarrays will have at most k distinct integers too, and moving either of the R1, moving R0 or R1 would cause will not increase the number of distinct integers. Therefore, for L+1 it is optimal to either not move them or move them to the right. Last thing we need to know is how to efficiently keep track of distinct elements in the current smallest and largest subarrays, satisfying the condition. If we would use hash map, insert would be of 1, but delete would be worst case of n. If we would use a ordered set, multiset, both operations will have a time, so delete would take O of log n, but insert would also take O of log n. Therefore, we can notice the constraints which say that each number can be at most n. Therefore we can use a simple array and when a count of element becomes is increased to 1, we knew it's a new distinct element, and when its count is decreased to 0, we know it is we know it is a new distinct element. When its count is decreased to 0, we know it is removed. It has been removed. This way we can easily count the number of distinct elements with O1 insert and delete. Time complexity O1, since each pointer will be moved at most O(n) times, and for each starting position we do O1 extra work, as mentioned, as mentioned in the last paragraph. Space complexity is O of n, since we have two arrays counting for counting the elements. Great. Post. I think this took me longer to write the editorial for than it took me to code this. It's just a painful 2 pointers problem, but nothing insane. Goodbye.